Hey, how's it going, guys? Today we're going to talk about another application of optimization, finding a point on a graph that is closest to another given point. Kind of an interesting thing. So we're just going to do a couple questions on this video. I'm not going to make it very long or terribly long, and I'll just kind of show you how this works. Okay, it should be pretty intuitive, but we'll see how this goes. So we're going to take this. We want to find a point on the graph y equals root x, which is a square root function, that is closest to the coordinate 3, 0. Okay, so if you know the square root function, it looks something like this. Something like this. This is what the square root function looks like. And 3, 0 will be some random point here, I guess. Call it right there. That's where 3, 0 is. Okay. So what I want to do is find the point on this graph. Remember, this graph is the equation y equals root x. The point on this graph that's closest to this point, so like right here, there's going to be some sort of value where this distance here is the smallest possible. Okay, this distance is the smallest, shortest possible distance from this point to this point, whatever. Okay, so this is going to be like an x. So let's call this coordinate here. If we call this coordinate x right here, let's say this is an x right here, we plug that in. Okay, this x value, if we plug it in x into this function, then the y value will just be root x. Okay, that's what it is. So this is the x value, this is the y value, which is this function here. So that's what's going to happen. All right, so here's what we're going to do. We're trying to minimize the distance. This is the distance here, and we have to make the shortest distance. So we have to use the distance formula to find a distance, and if you recall from geometry, the distance formula, and even pre-cal we've used it, is going to be x2 minus x1 squared plus y2 minus y1 squared. Okay, so in this particular case we have two coordinates. We have this one and this one. So I'm going to use those for my x's and my y's. Okay. So this will be my x2 will be x1. We'll call it. This is your we'll just call this my x2 there. So this will be x minus the other x, which is 3, and then this will be my y minus the other y, which is 0. So this will be root x minus 0, and then we'll square that. Okay, so from here we're just going to FOIL this. This is going to be x minus 3 times itself. Okay, so this is going to be x squared minus 6x plus 9, and then this minus this squared is going to be root x squared. I've already squared this part, so let's just keep going here. So this is going to be x squared minus 6x plus 9, and then root x all squared is just x, so I have this. So I will get a final answer here for my distance. This will be x squared. I'm going to combine the x terms, so this is going to be minus 5x plus 9. Okay, so we need to minimize this distance, optimize it by minimizing this distance. We need the optimal situation here from this point to this point. Okay, so we need to shorten this distance as possible. Okay, so what I need to do is I need to make a function here. Okay, a derivative of sorts, right? But the thing is, the square root function, right? We need to make this distance the smallest, but this distance right here, this is my distance, and this will be the smallest when what's inside of it is smallest, because this is a square root function. So to minimize the value of the distance, we need to minimize the value of what's inside the square root, is what I'm saying. Okay, because the smaller you can make what's inside the square root, the smaller that distance will end up being. So what I'm going to say is I'm just going to make a function here called g of x. And this will equal what's inside of this square root here, which is going to be x squared minus 5x plus 9. So if you remember the optimization steps I've shown you, what we need to create an equation for our first step, so that's going to be step 1. So we found it. Okay. Step 2 is, of course, to take a derivative and set it equal to 0. So we'll take this derivative, and this will be 2x minus 5. And we will set this equal to 0 and solve it. So what I'll get here is x will equal 5/2. Okay. The third step I told you to do is to check if it's a minimum or maximum, I'm going to use the second derivative. So I'm going to use g prime and take the second derivative test. So to do this part, we're going to take the second derivative. Here's the first derivative, which is 2x plus 5. So the second derivative will equal 2. Okay, so what we usually do is we'll plug in our critical points, these values for x, into this derivative, but there's really no point in doing that because what we're trying to see is what comes out, is it positive or is it negative. If your second derivative, if you recall the second derivative test, if the second derivative is greater than 0, then what we have is a graph that's concave up for the original function, so this is going to be a minimum. And if the second derivative is less than 0, then the whole graph for the original function is concave down, so it'll actually be a maximum. Okay, but as it turns out, this is guaranteed to be a minimum because the second derivative, right, is always positive. So since it's always positive, whatever you plug in there will be a minimum anyway, because this whole graph is concave down for the original function y equals root x, which is what that's telling us. So really this third step is often not necessary, but it still works. It's just sometimes you don't really need to work that hard to get this answer. This can't be anything else, right? So this is what I'm telling you. So here's the deal. So how do we find the answer? Okay, what's the point? We need to find this coordinate right here. That was the thing we're after, right? Well, we found the x value to be 5/2, so we know this x value is 5/2. We'll just plug it back into the original function, okay? Because it's a point on this graph y equals root x. Since x is 5/2, we're just going to plug it in to the function, and if I do that, the y value will end up being root 5/2, and this will be your answer, okay? That's kind of how you do this. It's a little trick for these root squared functions because you don't really need the square root to find the minimum distance. You can just make the derivative the inside and you can get rid of the square root. That's a little trick for this particular question. Okay, so there you go. We're just trying to minimize the distance. If you understood what I just did there, and I know that if this is the smallest it can be, then the distance will be the smallest it can be. So I just got rid of the square root and took that derivative. So your answer will be that. Okay, it'll be 5/2 and root 5/2. Okay, this next question probably a little more intuitive because it's just a line, and I'm going to do this two ways actually, because you can actually solve this question if you're clever without using calculus. Okay, it's possible, but I'm going to show you using calculus, and I'll show you a way where you could have avoided it. Okay, so find the point on the line 2x plus y equals 3 that is closest to this point, 3, 2. So this is pretty much a similar question to the one we just did, except instead of having a square root function, we have a line. So the first thing I'll do is I'll just go ahead and write this equation in slope-intercept form. Y equals negative 2x plus 3. Okay, I just solve for y here. Okay, so what I'm going to do is make a graph. You don't really need a graph, but it'll be good to see kind of what we're doing. It helps you see what's going on. So let's go ahead and just make a makeshift graph here. Graph, here we go. So we're going to say my y-intercept is 3, my slope is negative 2 over 1, so I'm going to go down 2 over 1, down 2 over 1, and something like this. Down 2 and over 1, oops. And this is going to be like a line, looks like that, of some sort, okay? So that's my function that I'm using. And there's another point out here in space called 3, 2. So if I go 3, 2, it's about right there. And what I'm trying to do is figure out, this is the object of the question here, I'm trying to figure out what is this point right here, whatever it is, that gives you the shortest distance to that point, okay? I want it to be the shortest possible distance, so what is this coordinate right here, okay? And I don't know that coordinate, we could call it x and y again. Of course, if I plug it in for y, if I plug in this x here, this will just be negative 2x plus 3. It's the same thing as the function. So this is the other coordinate I have. Okay, we could do this exactly the same way as we did the previous question. We could use the distance formula. Okay, so the distance here would be equal to the square root of this coordinate I know is 3, 2. So we'll just do x minus x. So we can say x minus 3 if we want. Which point we goes first doesn't make any difference. We can say x minus 3 all squared again. And then in this case I can say 2x plus 3, which is your first y value, and we'll subtract 2 from that. And then we'll say all squared. Okay, same sort of thing. So what I'll do here, same tricks, okay? So we're going to FOIL this out. It's going to be x squared minus 6x plus 9. And then I have to square this. Before I do this, I'm going to say that this part right here is actually, it's going to be, let's do this here, negative 2x plus 1. And I'm going to square that. I'm going to multiply that by itself, is what I'm going to say, okay? Because 3 minus 2 is 1 anyway. So if I FOIL that out, what I'm going to end up getting is I'm going to get, let's see, I get 4x. Oops. This thing is temperamental. The smart board has got a huge delay. My computer's very slow. We have 4x squared. We have minus 2x, so that's minus 4x, and then just plus 1. So that's going to go right here. So we got this 4x squared minus 4x plus 1. And then that's that. So we've squared both of these. So now we're going to combine our like terms and simplify this for our distance. Okay. So our distance here. I wish there wasn't such a delay. It's hard to write when the computer's a half second behind your writing, but we'll see what we're going to do here. X squared, this is going to be 5x squared. Negative 4x, negative 6x, so it's negative 10x, and then I got 9 and 1, which make 10. Okay, so that's what I have here. This is my my distance here. So as I said before, you can shorten this distance by minimizing what's inside of the square root. If we can minimize what's inside the square root, that will give you the smallest value for the distance. So we can ignore, again, as a little trick here, we'll ignore the square root and we'll just make a function of what's inside. We'll call it g of x or something, okay? And we'll say this is equal to 5x squared minus 10x plus 10. So that's my step one, make a function that you intend to use to optimize. So this represents, I know if I can shrink this possible, this function here, if I can make it as small as possible, or minimize it, in other words, it'll minimize that distance. That's what I'm doing as a trick. So here's the deal. We'll take our derivative as our second step. This will give me 10x minus 10. We've set that derivative equal to 0. Solve for x. So that means that 10x equals 10, and x would equal 1. As a third step, what we like to do, just to be sure, is we will use second derivative tests. Okay, so we'll check if this is a max or a minimum, is what we're doing. Check if, I'm actually checking to see if it's a minimum, because that's what I want it to be. So, as I said before, if your second derivative, we're going to use a second derivative here, we're going to find g double prime. If your second derivative is positive, it's a minimum, and if it's negative, it's a maximum. That's what I'm saying, okay? So we'll take the second derivative, what's the derivative of this, which is just going to be 10. So as you can see here, there's no critical value. Here's my one critical value, but if I plug this into here, it doesn't matter if I plug it in here because the answer is still going to be 10 no matter what. So this is guaranteed to be a minimum, okay? There's no maximum I can find. I'm sorry, yeah, it's guaranteed to be a minimum point. There's no maximum point that I can find here. So that's the trick. So we don't, this part's extraneous, but you didn't really need to do it, but this is going to give me my smallest possible, this is going to be the coordinate of this point right here. This is the shortest possible distance here. This coordinate right here for this point will be a 1. Now how do I find the y value? I'm going to plug it into the original function for this line, which is negative 2x plus 3. So what I would get is negative 2 plus 3, so this is also going to be a 1. So my answer for this coordinate, what is this coordinate here? Let's write this here. What is this coordinate right here that'll give me the shortest distance? This coordinate will be 1, comma 1. That's how you find this answer using calculus, okay? Now, because this is a linear function, we could have actually done this without using all this work here or all this calculus. We could have used some common sense and the properties of lines. So I'm going to do that now. And you can keep watching if you want to see that. Okay, but this isn't applicable to all situations, but it is applicable to these sort of linear situations that you get, which are not very common anyway. But here's the deal. Since I'm looking at this graph and I already have it drawn, I know that this shortest distance here, for this to be the shortest distance, this needs to be a right angle. These two graphs, if I were to make this a line connecting these 2 points, they would have to be perpendicular. That's just common sense, okay? Because the shortest distance is a straight line, and that shortest distance will make a line that's perpendicular to the other one. So here's what I need to know. I know the slope of this line is -2, or -2/1. So the perpendicular slope will be the opposite reciprocal, will be +1/2. So I can make an equation of this purple line, and I can say this equation would equal 1/2 x plus b. I could do that. Okay, and since I know that this coordinate 3, 2, since I don't know the other coordinates, pretend I don't actually know this is 1, 1. I know this coordinate that's given, this 3, 2, is on this point. So we know it's on this line rather. So we know 3, 2 is a coordinate. So we can just plug it in for x and y and solve for the unknown b. Okay, so we've done this before. 2 will equal 1/2 times 3 plus b. Again, hard to write when the delay is so big for this, but there we go. Alright, so if I do this, this 2 is going to equal 3/2. Good grief. 3/2 plus b. So b is going to equal 2 minus 3/2. 2 minus 3/2. And that's going to be the same thing as 4/2 minus 3/2, which is again 1/2. That's going to be 1/2 when I sort that out. Okay, so that's 1/2. So now I have an equation. Okay, here's my equation. I know I'm going to plug this back into this unknown value for b. So this equation is going to be equal to 1/2 x plus 1/2. Here's a way you could have done it. So this is the equation of my purple line, and I already have the equation of the blue line is -2x plus 3. So I'll just set this equation here equal to this equation here and figure out where they intersect, and that will be the point that I was after, as it turns out, for the answer. And what should happen, if this is done correctly, is I should get the answer as being 1, 1. Okay, so let's make sure that's correct. So I have -2x plus 3. This will equal, good grief, I wish I could write on this, equal 1/2 x plus 1/2. This is why I use the iPad, because if I use my computer, it's actually really slow. Okay, so here we go. So to solve this, I'm going to multiply everything by 2. And then I will subtract x from both sides and subtract 6 from both sides. And x would equal what again? It would equal 1. And then all I have to do is plug this 1 into either equation. If I were to plug this 1 back in here, I would get 1 times 1/2, which is 1/2 plus another 1/2. So the y value would be also what? It would be 1 as well. So what I would get is 1, 1 for my intersection, which is the same thing as the answer to the question. And as you can see, which I already knew, these answers will be the same. So if you actually had the patience to watch all that, I applaud you. Thank you for watching. But you're going to have some questions on your homework about finding shortest distance, and that's the way to do it. Okay, I've done a couple examples. What you do is you use a distance formula typically, and then you'll just take what's inside of it and make it its own equation, take its derivative, and so forth. But anyway, hope that helps you out, and thanks for watching.